Hello and welcome to Business Calculus Screencasts. In this screencast, in section 1.1, we'll specifically focus on lines, but more importantly on slope, or how fast the quantity is changing, because this will be very important later when we study the derivative. In fact, it will be the slope of the tangent line, and how we'll find out about the slope and how we used to calculate it would be specifically the slope of the tangent line. And the one variable that we use is small m. That's how we'll refer to the derivative from now on. Let's take a look here. I have a nice little handy graphic for you guys. The slope is basically change of y over change in x, or very specifically how we used to compute it. It's y2 minus y1 over x2 minus x1. And notice how there's a change in y, there's a vertical change, and change in x is typically the horizontal change. And how do they measure accordingly. So let's take a quick look at a few examples. For example, if we're trying to find the slope passing through the 2 points, well, basically we can compute the change between the two y values, 2 minus 5 over, say, the change in x values, negative 1 minus 4. So we'll get negative 3 over negative 5, which will get 3 over 5. So very quick and easy, I suppose, review from. Let's take a look. What if x is not changing, but y is changing? It's a very specific line. If you try to graph it, actually it's a vertical line. So note, we can compute the derivative the same way. Notice there is a change in y, it's negative 11, but the change in x, you get 0. And what happens when you divide the number by 0? Well, we can't. You know, from algebra, you probably remember that the slope is undefined. But something that we'll use in this class is that it will actually be infinite. Why is that? Because imagine if you're dividing a number by a very small number, maybe not 0 exactly, but something like 0.001, then you'll get a very large number, or in this case, you'll get a large negative number. So what will happen is you'll have an infinite slope, and that's what happens with vertical lines. You'll have an infinite slope. So here's that example. So this is a vertical line. Slope is undefined or infinite in this case, as the incline is a little too steep. Remember how slope is related to the incline, essentially, from left to right. All right, let's take a look at equations of the line, which will be important for us also. For example, y equals mx plus b may be familiar to you because it's a slope-intercept form. M, which is the constant in front of the x, denotes the slope, and b denotes the y-intercept. So if we have an equation finding the slope, if it's in slope-intercept already, like y equals 2.5x, should be very quickly to find slope. Slope is 2.5, the variable in front of the x. And the next example, what if it's not in a slope-intercept form? Well, in this case, we would need to solve for y, and that's how we can find the slope. So we need to put it in the slope-intercept form. How do we do that? We solve for y. So notice how you can move the 5x, subtract the 5x from both sides. Then you can divide by 9. So we'll get 5 over 9x minus 11 over 9. So what is the slope? You can probably see it. It's 5 over 9. Okay? Let's take a quick look at what if we have certain information, say a point and the point and the slope. So what we can do, intercept form, one way to do it, well, you can plug in y equals mx plus b and then solve for b because we don't have the y-intercept in this form. But another one that I like to use is the equation of the line and point slope form, which is y minus y1 equals to, let me write this down, equals to m times x minus x1. Okay, so very easy to use it. It's y minus the y of the point equals to the slope, negative 2, times x minus the x of the point. And here we can solve for y and essentially put it in slope-intercept form, because with slope-intercept form, the equation is unique. We'll only have one equation. Notice how I am solving it here. So you can distribute negative 2 And on the next page, you can also add 3, I believe. So we'll get y equals negative 2x plus 5. Okay? Then, what if we have an example and we're trying to find an equation of the line passing through 2 points? Well, we can do it similarly. We can find slope, which I have over here. So I try to set it up and see if you get the same slope. And you can use either one of the 2 points. I decided to use the second one. It seemed a little bit easier, which is why we don't want to leave it in this form, because what if you use a different point, then you'll get a different answer. So that's why we want to solve for y. And no matter which point you use, you should get the same answer. So I set it up right here. And it's the same way. You should be able to distribute the negative 1/3. You'll get a little fraction work here. Then you would add 9, which is, you would add 3, which is 9 over 3. And this is how come we'll get 10 over 3 right here. Now let's take a quick look at few applications. So hopefully the equations of the lines are coming back to you from previous algebra courses. Now here's a couple of interesting applications. If you like exercising or you like going to the gym, there is something that they recommend is that there is a certain quantity called target rate zone. Is if you do enough cardio to get your heart rate up into the zone, then you're getting the optimal exercise. That's what I hear. I wonder how exactly this formula is. Well, it'll be interesting to find out. So I'd recommend you research it. But here's what we're given. To achieve the maximum benefit for the heart when exercising, your heart rate in beats per minute should be the target rate zone. The lower limit of the zone is found by taking 70% of the difference between 220 and your age, and the upper limit is found by using 85%. Okay, so let's scroll down a little bit. So now we want to find the formulas for the upper limit and the lower limit. We'll call them U and L as linear equations involving age x. So note how I set up the upper limit here. U is equal to, well, this is how we find percentage typically. So let's take the difference, 220 minus x. So to find the percentage of it, we'll multiply it by 0.85. And then what I did is I distribute 0.85, and so we get 187 minus 0.85x. Now you can do it similarly with the lower limit. You can try to set this up right now, maybe pause this video. So note how I did the same thing with 0.70. I distributed, and so we get 154 minus 0.7x. So these are the 2 equations. Now let's do some problems. What is the heart rate for a 20-year-old and a 40-year-old? How would you find this information? Now let's take a look. For a 20-year-old, what I have done is plug in x equals 20 into both equations. So what I got was for the lower limit, I got 140, and for the upper limit, I got 170. So notice for 20-year-old, it's quite high. For a 40-year-old, it's a bit lower. So again, I plugged in x equals 40 into both upper and lower, and I list the lower one first. So it's from 126 to 153 beats per minute. Now let's take a look at a different problem. Here is a problem on immigration scenario. Let's say in 1950, there were 249,187 immigrants admitted to the United States, and in 2008, the number was 1,107,126. Assuming the change in immigration is linear, write an equation expressing the number of immigrants y in terms of t, the number of years since 1900. Now note this number is important, since 1900. So what happens there, note how we have 2 pieces of information above. In 1950, so that gives us a time and a y. And here we have 2008, and we also have a y. So note how we have 2 points where we can write an equation of the line. So let's see how I set this up. So we do have 2 points. So what I did was, since it's number of years since 1900, I subtracted 1950 minus 1900. That's how I get 50 years. And we have that number, 249,187. And second number is 2008 minus, it's 108 years since 1900. And we have the y also. So we can set up the slope. So I got the slope to be 14,792.05. And I decided to use the first point, which seemed a little easier. So I set this up as y minus the slope times t minus 50. And so we have y equals to 14,792.05 t minus 490,416. Okay, so what we did find was the linear equation. Now what's next? We used the result to predict the number of immigrants in 2015. Well, what I did, the t is 115 years since 1900, and I plugged it into the equation above to get this result. Obviously, the number of immigrants cannot be decimal, so what I did was round it up to the nearest number. Okay. Now, here is part C. Considering the y-intercept in your answer A, discuss the validity, if you've taken statistics, you probably heard this term before, of using this equation to model the number of immigrants throughout the 20th century. Well, if we look above in this equation, notice how the y-intercept is negative, which doesn't quite make sense. It's not like there was a great exodus of immigrants in 1900, so it doesn't make sense. So something about this model is off. Well, what's the problem here? Well, it turns out that we only have 2 data points. We don't actually know that the data is linear. What if we have more points and it's not linear? What if it's exponential? And so the problem is, since we only have 2 points, it's said in part A to assume it, but we cannot assume it in general, of course, unless we have more data, which is here's where my answer is. Since it's negative, it doesn't really make sense. And the model is not valid since there are only 2 data points, and the model growth may or may not be linear. So more data is needed to draw a conclusion. So that's it about the first section. So look for linear functions in the next screencast.